Hello guys, I'm recording this video in Korea. So, so, so we will learn about the chapter 6 of the textbook. So, as I mentioned in the previous class, so actually this chapter number 6 is the chapter number of the textbook. And then, so also, the final exam will cover the chapter 4, 5, and 6 of the textbook. Yeah, so it means textbook at the slide number. So, so you need to know that. So, in the final exam, so so we will cover the chapters 4, 5, and 6 of the textbook. Okay. Okay. Let's learn about the today's topic. So today's topic is the parallel processors. Okay. So, what is the parallel processor? What is a parallel processor? So what is the meaning of parallel? So parallel means that so we can execute multiple ins multiple something, multiple things concurrently or simultaneously. So computer systems, when we mention parallel systems, so it means that these parallel systems can run the multiple tasks concurrently. So how can we implement parallel computer systems? So until now, so we learned about actually the single process architecture, single core process architecture. So what does that mean? So we learned about the process architecture in chapter 4. So it's the process architecture, processor. It's a chapter 4. And then we learned about the memory hierarchy, right? So it's a memory hierarchy. This is the memory system. So we learned about the memory hierarchy in chapter 5. So, but when we learned about these systems, these computer systems, so these computer systems, this computer system is composed of one processor core and one memory system. Okay, so actually the memory hierarchy is working with the one core, so which means one CPU, right? But how can we implement a parallel computer system? So I mentioned that in a parallel computer system, we can run multiple tasks, so multiple tasks concurrently at the same time, right? So how can we implement? So how can we implement these parallel systems? So obviously, so we can increase the number of cores. Okay, so cores. So when I mentioned the cores, so cores means some independent CPU. So and then independent CPU, so we can assign uh thread, right? We can assign a thread in independent cores. So which means we can run the multiple thread in these multiple cores or multiple CPUs. So how can we implement the parallel computer systems? So we can increase the number of cores, and then using these multiple cores, we can run multiple tasks. So you can find the task level parallelism, which means that we can run multiple tasks concurrently, right? So it's a processor level parallelism. So when you mention uh, the parallel processors, so it means that we can run multiple tasks concurrently. So how can we implement this system, these parallel computer systems? Also, in order to utilize our parallel computer systems, so we need to also use parallel programs. What does that mean? So think about the matrix multiplication. So so actually, when we write a matrix multiplication code, then we can just generate a single binary, right? And then when we run this compiled single binary file, then only the one thread will be generated, and then this thread will be assigned to a certain CPU core, right? It's a core, and then a core will run the assigned thread. So this is the single-threaded application. But when we write matrix multiplication code, so we can also generate the multi-threaded applications. So which means that the matrices matrices are partitioned into multiple submatrices, and then actually each thread is computes the multiplication of the submatrices, right? So it means multiple threads are generated, and then when we run this matrix multiplication application, then the multiple threads are assigned to the multiple processors. So and then we can run this application. So what is required? Parallel programming. Parallel programming is also required, and then in order to design a parallel program, then we need to apply parallel algorithm. Okay, so this is also in order to implement parallel computer systems. So which means we need to also implement the multi-core architectures. Also, the software needs to be designed for these target parallel processors. So which means the hardware and the software design is required. Okay, so as I mentioned, so the hardware, when you mention a parallel computer system, then we can just categorize the hardware as the serial computer system or parallel computer system. The example of a serial system is the Pentium 4. So it's a very old CPU. And then Pentium 4 just includes a single core, so which means CPU chip, in a CPU chip, there is only a single CPU core, right? And then that's what we have learned in this course, right? And then what is the example of parallel processors? So example is the quad-core Xeon processors. So this Xeon processor is also the old generation CPUs, which means so as you can see, this Xeon includes only 4 cores, and then actually the modern CPUs actually includes the multiple cores, right? And then so we can say that the modern modern computer systems are actually parallel computer systems. And how can we categorize the software, like the sequential software? So it means that it's a single software will generate only one thread, right? So the example is the matrix multiplication program that's the single uh, for single thread. So it's a very common and then very nice matrix multiplication implementation, right? And then, so we can also define the concurrent software. So as I mentioned, this concurrent software or parallel software generate the multiple threads, right? Then these multiple threads are running concurrently. So concurrent means that it's at the same time, right? The example of a concurrent software is operating system, right? So then, so we expect that. So when we design parallel computer systems, so which means that my computer hardware includes the multiple cores, right? So which means that so using these multiple cores, we can run multiple tasks or multiple threads concurrently. So which right. So what does that mean? So using a parallel processor, so we can improve the performance. So usually, we can improve the performance of the throughput of a computer system, right? But uh, there are challenges, right? So, so actually, even though we increase the number of cores in a CPU, but the performance cannot reach the performance is not proportional to the number of cores. So this issue is called the scalability issue. So scalability issue. So scalability issue represent that. So for example, if we just use four-core system or four-core CPU, then we can expect that the performance can be improved by 4 times, right? That's our expectation because the multiple threads are the multiple threads can be run by these multiple cores concurrently, and then our expectation is that 4 times of performance improvement. But it's not true actually. It's not true in the real world. So why? Because of some issues, the performance is lower than the 4 times. And then this performance issue is called scalability issue, right? So then why cannot reach the scalable performance with the multi-core systems? So we will learn about the challenges. Okay. So parallel software is the problem. So what does that mean? So actually, the not to improve the performance, we need to guarantee the scalability of the target system. Then, so this is the original task, right? It's an original single task. Let us assume that this is the original single task, right? And then, in order to utilize the performance of the multi-core systems fully, then these tasks need to be perfectly partitioned into the same number of the the it's the same number of cores, which means if we use the 4-core CPUs, this task needs to be partitioned into 4 tasks perfectly. So perfectly means that so 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 it's a perfectly. So every part can be parallelized. Okay, but it's not easy actually. So So it means we need to develop a very perfect parallel algorithm for designing these perfect parallel applications. Also, there are some other issues such as I just explained about the partitioning issue. So which means that it's not so our task our task is not always partitioned into multiple parts. Okay, so usually our task is composed of parallelizable part. So which means that some part can be partitioned, but some part is not partitioned, right? So it means that the result needs to be gathered, and then the gathered result are need to be gathered result need to be processed sequentially. So this is the sequential part, right? The sequential part. And then this is the parallelizable part. So this is the partitioning issue. Also the coordination. So actually if the tasks are partitioned into multiple parts, then it is partitioned these partitions need to be cooperated. Okay, but it's not always easy, right? And then another issue is the communications. Sometimes the parameters need to be uh, shared by, also some data are shared by multiple partitions. But so for this for this then data need to be shared also the communicated between the multiple thread or multiple partitions. But it takes time, right? So we require some communication protocols for this data communication. So these are some challenges for parallel programming. And then because of this overhead, then we cannot, it's not easy. It's not easy to implement scalable systems, right? So scalable system is that, so, so which means if there are 4 cores, and then the performance can be improved by 4 times, but it's not easy, right? Because of these challenges, okay? Okay, so now, so let's learn about the Amdahl's law. So Amdahl's law explains the difficulties of this scalability, okay? So Amdahl's law, so it's actually this is the very important law in computer architecture field. And then, so it's not difficult, right? It's not difficult, but it's very intuitive, and then it's so straightforward. Okay, it's straightforward. It's not difficult. Okay, so Amdahl's law explains sequential part can limit speed up, multi-core architectures. Okay, so what does that mean? Our task. So this is the task, some task, but this task can be composed of parallelizable part. Okay, it's a parallelizable part, and then sequential part. So parallelizable part means that so the tasks can be partitioned into multiple independent tasks, right? And then these partitioned tasks can be assigned to the multiple cores. But the sequential part means that, oh, this part cannot be partitioned. So this part needs to be executed sequentially. Okay. So when you analyze the execution time of work code, then we can categorize it. So this is the execution time, right? And then this execution time can be uh, split into parallelizable part and sequential part. Okay. And then when we apply the multi-core architecture, then which part can be improved? Obviously, this part. Only this part can be improved by multi-core architecture. And then if we assume this part, the parallelizable part, can be perfectly parallelized, and then if we just apply N-core architecture, then we can reduce the execution time for this parallelizable part as the T, T parallelizable divided by N, right? Right? Oh, so it's very, very simple. It's a very simple uh, assumption, right? But okay, so it's a Amdahl's law. So we can only improve this part, the parallelizable part, right? So this is the Amdahl's law. And then this is an example. So, let us assume that we have 100 processors, and then we want to achieve 90 times of speed up. Then what is the fraction of the parallelizable part for this condition? Okay, so the execution time, new execution time is the t parallelizable. So t parallelizable divided by 100 because this is the number of cores, and then we assume that the parallelizable part can be perfectly partitioned. But sequential part cannot be improved by these 100 processors. And what is the speed up? Speed up is 1 over 1 minus f parallelizable, right? So it's the fraction of a parallelizable part. Okay, so f parallelizable is the uh, p execution divided by p parallel. So for the original task, right? So only this part can be reduced, and then it should be 90. Okay. Then if we just solve this simple equation and f parallelizable, so that is the fraction of the parallelizable part is to be 0.999. So what does it mean? So in order to achieve, so we cannot achieve the 100 because of this sequential, but in order to achieve the 90 times of speed up using 100 processors, then only the sequential part needs to be 0.1% of original task. Right? What does it mean? It means that the most of tasks need to be parallelized, right? In order to achieve this amount of speed up, right? This is so, which means so actually because of a sequential part, so because of this sequential part, the performance improvement by the parallel processors is limited. So this is the Amdahl's law explains this. Okay. So this is the example. The workload is composed of a sum of 10 scalars and then 10 by 10 matrix sum, right? So and then we can just compare the speed up from 10 to 100 processors. Okay. So this workload is composed of 10 scalars. So what does that mean? What does that mean? This is the scalable sequential part. Okay, and then 10 by 10 matrix sum. So 10 by 10 matrix sum, it can be parallelized. Okay, this is a matrix sum, right? So 10 by 10 matrix includes the 100 elements, right? So using the single processor, the execution time is 10 scalar sum, and then 100 matrix sum. Because there are 100 elements, then the execution time is 10 plus 100, and then multiply by execution time of add. Okay. How about the 10 processors? This part cannot improve, right? Because the scalar addition is the sequential part, right? We can improve only this part, right? So if we just use the 10 processors, then this part is just divided by 10, right? So the total execution time is 20 multiplied by execution time of add. What's the speed up? Speed up compared to the single processor. So 110 divided by 20 is the 5.5. So our expectation, so because we have 10 processors, so our expectation is that the speed up is 10, but the speed up is just 5.5. So it means the 55% of potential, right? How about the 100 processors? So this part is improved. It's the 11 multiplied by execution time of add. So it's a 10. So if we just compare the performance with the single processor, then it's the just 10. So it means the 10% of the potential, right? So even though we increase the number of cores, so it is the linear, our expectation is that the performance can be proportional to the number of cores, but actually by the Amdahl's law, and then also it depends on the fraction of parallelizable part, but in the Amdahl's law explains that the performance is saturated because of sequential part. Okay, so which means the sequential part limits the performance improvement of multi-core architecture, right? That's Amdahl's law explains. So, but if the matrix size, so it means that parallelizable part can be, if the parallelizable part is increased, then we can benefit from multi-core architectures, obviously, right? So for the single processors, so total execution time is like this, right? But if we use the 10 processors, then this parallelizable part can be reduced. So the total execution time is like this, and then speed up is 9.9. So we can achieve 90% of the potential speed up. How about the 100 processors? So this part is divided by 100. Okay, so it's the total execution time. So we can achieve the 91% of the potential performance improvement. Then what can we observe? So we can observe that. So by Amdahl's law, if we increase the fraction of the parallelizable part, then we can benefit from the multi-core architecture more. And then obviously, right? So actually, this is called the weak scaling. So we can just categorize the strong scaling and weak scaling for the parallel processor architecture. So strong scaling means that assume that the problem size is fixed, right? So which means, so like this Amdahl's law, so we just fix the problem size. So it means a sum of 100 scalars and then 10 by 10 matrix sum. And then this is fixed. And then we will learn this fixed workload on the multi-core architecture. So this is the strong scaling. But weak scaling. But we can also, like this example, in order to benefit from the parallel processor architecture, we can also increase the fraction of parallelizable part, right? Like this. So with scaling means that problem size is proportional to the number of processors, right? So actually, if we just assume the strong scaling, then the multi-core process architecture is not a good solution, right? So because the performance is limited by uh sequential part, right? And then as I mentioned, performance is actually saturated even though we increase the number of cores. So it's pessimistic, right? Actually, so Amdahl's law explains that, oh, multi-core architecture is not good. It's not a good solution. But actually, if we use a multi-core architecture, then the problem size is also proportional to the number of cores. So which means that think about the server computer systems. So if we just increase the number of cores in a server computer system, then the server computer system can actually handle a more concurrent thread, right? So and then we can also increase the number of thread handled by these servers, right? So the weak scaling just assume that the problem size is proportional to the number of cores. So in this assumption, then the performance is also proportional to the number of cores, right? Okay, and then so actually, modern computer systems, there are many concurrent threads. Many concurrent threads are running, the modern computer systems. So, which means we can benefit from multi-core architectures. Okay, but you need to also understand the Amdahl's law. So, Amdahl's law actually explains some very uh, important aspect in the computer architecture, right? So the law explains that so we need to uh, focus on the common case, okay, not the special case in a computer architecture. Okay. Okay, so I explained about the Amdahl's law, and then as I mentioned, the Amdahl's law is an important law in computer architecture field. So I hope every student can understand the Amdahl's law. Okay. And then, so let's learn about the relation between instructions and data. Okay, so uh, we can classify a computer CPU, okay, the computer processors using the class of instruction streams and the class of data streams, right? And then actually this is called the Flynn's taxonomy. Okay, so taxonomy means that we can classify some targets or some target systems, right? So it is the meaning of taxonomy. So Flynn's taxonomy just defines uh, the, the processors based on the class of instruction streams and the class of data streams. So then we can classify the instruction streams as the single instruction or multiple instruction, and then data streams as the single data and multiple data. And then, so by combining these instruction streams and then data streams, then we can classify processors. So for example, single instruction and single data. So it means a single instruction just to handle scalar data, okay, single data. Then that's what we learned in this course. And then this example is the Intel Pentium 4. It's the single core architecture, which means using the single instruction just to handle the scalar data, single data stream. Okay, so it's called the SISD. Then also using the single instruction can handle multiple data. So for example, using a single instruction can handle vector type data. So what is a vector? A vector includes multiple elements, right? So when we execute the vector type instructions, then a single instruction, this instruction handles multiple data streams. So and then this type of processor is called SIMD processor. So SIMD, okay? And then example is the SSE instructions in x86 CPU, right? So it's a vector type processor. Okay? It's called the SIMD processor. MISD, it's not equivalent, okay? So multiple instruction and same data, no, no, no examples. And then also another example is the MIMD, so multiple instruction and multiple data. This is the multi-core architecture. So which means so we can run the multiple thread concurrently. This is called the MIMD. Right? Example is the Xeon CPU, right? The multi-core CPUs. Okay. So based on the relation between the instruction stream and data streams, we can classify the processors. Okay. So as I mentioned, the vector processor just handles the vector type data. So the RISC-V also has the vector extension. Okay. So in the vector extension of the RISC-V, and there's the vector type registers, right? Like register number B0 to B31. And then also RISC-V supports the vector type instructions. So you can find the postfix.p, so which means that it's the vector type instructions. Okay? So vector processor is the example of SIMD processor. Okay, so police taxonomy is also important. Okay, so based on uh, uh, the class of input streams and then uh, data streams, we can classify uh, processors based on the police taxonomy. Okay, so this is the example. Okay, so it's a conventional RISC-V code, but using the vector type extension, and we can just use the instructions like this. Okay, and we can instead of this loop, then we can just handle the vector time instructions. So what is the benefit? So if we just execute this conventional RISC-V code, then in order to compute the multiple elements, then we need to execute the multiple instructions. You can find the iteration loop here, right? This is the iteration loop for computing the multiple elements. But if we use the type instructions and then the type data, then we can just reduce the number of instructions. Okay? So as you can see, the program is very simple, right? So by doing this, we can increase the performance. Okay, this is the benefit of SIMD. Okay, so here's the modern processors, so includes the vector extension, vector type instructions. So it is because uh, vector type instructions are frequently used for multimedia applications, right? And then, so our computer systems run multimedia application frequently, which means the performance of the multimedia applications can be improved by vector type instructions, right? So, so we learned about the police taxonomy, and then we briefly learned about the vector processors, and we learned about the hardware multithreading. The hardware multithreading means that using a single core and single core can run multiple threads concurrently. So this is the meaning of the multi-thread hardware multi-threading. So how can we implement this hardware multi-threading? What is required? So if you see the compiled code, and compile the code so that so binary code, you can find the program counter, right? And then also these instructions just handle registers, right? So which means if we just if a single CPU includes multiple program counter and then multiple registers, then we can run the multiple thread concurrently, right? So and then actually the modern processors include multiple processing units. So you mean such as the ALUs, right? So if we so which means if we just use the multiple registers and the multiple program counters, so if we just increase the number of these components, right? Then it means we can utilize these multiple processing units using the multi-threading. Okay, so this is the idea of multi-threading. And then actually the Intel CPU and the AMD CPUs actually can support the multi-threading. So we know the brand name of the Intel multi-threading is the hyper-threading, right? Hyper-threading. So it is the brand name of Intel's multi-threading. Okay, so like this. So this is the uh, example of a multi-thread. So this is the some thread A, thread B, and thread C, and thread D. Then we assume that we want to run this multiple thread in a single core. Then we can also define some different multi-threading mechanism like coarse-grained multi-threading and fine-grained multi-threading and simultaneous multi-threading. It's called the SMT. Is the simultaneous multi-threading. Okay, so coarse-grained multi-threading is that the thread is changed when a thread encounters cache miss. So in this example, the thread A is executed, but thread A just encounters a cache miss at this point. In this case, then thread B is executed. So when a thread encounters a cache miss, then it will take time. It will take many cycles until the data is fetched from the main memory, right? And then the pipeline is stalled. Then the CPU just change it to the next thread, so thread B, and the CPU can execute the instructions in thread B. The fine-grained multi-threading is that the threads are changed every clock, like this. And then simultaneous multi-threading, so it just uh, execute instructions using the available slot, right? In this example, thread A increased the multiple two instructions, thread B equals the three multiple instructions. Then SMT just uh, assign the instructions to the available slot like this. So this is called the simultaneous multi-threading. And then intense hyper-threading is actually simultaneous multi-threading. So multi-threading is an approach that can handle they can address the performance issues by uh, the cache misses actually, right? And then so by doing this, we can increase the number of instructions executed by CPU, right? So by doing this, we can improve the performance. So this is the multi-threading idea. Okay. So and then for the GPU, I will skip this part. And then if you are interested, then you can take the GPU course actually in the graduate level. Okay. So The GPUs are very popular recently because of AI applications, right? Right, because of AI application. Okay, so I also skip the performance model. So it is just explains the loop line model. So this is a kind of some advanced part. So I will explain about this loop line model. Okay. So in chapter 6, so I explained about uh, the concept of parallel architecture. And then I explained about the Amdahl's law. So the Amdahl's law is very important in computer architecture field, right? And then I explained about the Flynn's taxonomy, right? And then I briefly explained about the multi-threading, hardware multi-threading. Okay. So actually, in this course, we have focused on the single core architecture. So which means the parallel architecture is I briefly explain about the parallel architecture, but it's just a brief explanation. So actually, the parallel processor architecture uh, include the many challenges and then many research items. Okay, so the parallel architecture is more complex, more complex than a single core architecture. And then, as I mentioned, there are uh, many challenges. So many challenges in the hardware aspect, so many challenges in software aspect. Okay, so but so we can improve the performance using a parallel architecture, right? So think about the GPU. GPU includes many cores compared to the CPU, but but GPU is designed for parallel processors, parallel programming, the parallel applications, right? So we know, we know that GPUs are good for AI applications, but it is because of the characteristics of AI applications, right? So, and then actually the GPU is not good for the serial applications, like the normal applications such as uh, the operating system and the normal uh, like normal applications that can be run on the CPU. But these applications are not good for the GPU. Okay? So actually, we need so actually in this course we learned about the basic things of computer architecture, right? So so I will close the this course. So in this course we explore the computer system architecture at an abstraction level. Okay, so we have focused on the microarchitecture level and then architecture level of the computer systems, and then we just learned about the basic concept. Okay, it's just the basic concept. So, as I mentioned, the modern computer systems are very complex. But in this course, we learned about the basic concept of computer systems. We did not learn about the out-of-order processors, so superscalar and the branch prediction, speculative execution, cache coherence, memory consistency, perpetual storage system, blah blah blah, FPGA. So actually, as I mentioned, the modern computer systems are more complex. But in this course, we have learned about the very basic concept, very basic knowledge on computer architecture. And then uh, the current CPUs includes the more complex architectures such as out-of-process architectures, also superscalar and then speculative execution. And then these techniques, these architectural ideas are essential for improving the performance of computer systems. Okay, so this, the CPUs and then GPUs are actually very complex uh, system, very complex, includes the very complex architectures. But we didn't learn about these complex architectures. So if you are interested, then you can take the advanced computer architecture course. So now, so this course is provided for graduate students. But so actually, if you are interested in computer architecture, then you can take the course. Okay, okay, so I believe you can just explain about these questions, right? 자, vero, it's CPU sana, vero. Okay. And then if you're interested, then you can click this link, and then this is the Turing Award lecture from ISCA 2018. The Turing Award is very uh, it's an important award. It's like the Nobel Prize in computer field, computer engineering or computer system field. Okay, so in this lecture, the Turing Award recipient, so those are uh, David Patterson and then John Hennessy. Those are authors of our textbook, right? So these legendary guys in computer architecture field uh, explained about the history of uh, the RISC CPUs, then also some friends in the computer architecture research in this lecture. So if you are interested, then you can click this link, then you can watch the YouTube video, and then you can also watch the Turing lecture by David Patterson and John Hennessy. Okay, and then they explain about the golden age of for computer architecture. So which means, so the computer architecture is the fundamental part in the computer systems. It is because so actually the software, as I mentioned, the software runs in a virtual virtual world. So, so we learned about the virtual memory, right? So software, actually the software applications run on fake world, a virtual world, right? But computer architecture is the is the interface between software and hardware. So which means we also need to uh, know about the real world aspect, like the real hardware and real hardware architecture or real system architecture. Also, we also need to support some execution of software like the fantasy world, like virtual world. Okay, so actually, the computer architecture is the fundamental part, computer systems. Okay, so that's why. So nowadays, you know computer systems are changing because of AI applications. So which means, so to accelerate the AI applications, then we need to uh, design um, some improved hardware architecture. Okay, and then upon these hardware architectures, then the AI applications can run. Okay, so that's why the computer architecture is the fundamental part in the computer systems, right? I hope everyone can understand some of this aspect. Okay, so and as I mentioned, to improve the computer systems, then we need to learn about the software part and then the hardware part. Okay? That's why the computer architecture is the important study. And then that's why this course is the mandatory course in the computer science department. Okay? Okay. So if you're interested, then you can contact me about some research ideas. And some, okay. Yeah. So for this semester, then I believe that every student have studied very hard for this course. And then thank you for your time. Thank you for your effort. And then also thank you for your attention for this course. Okay. And then good luck for your final exam. So we have only the final exam in this for this course. Then this is the very important part for your grade. Okay. So, okay, I closed this course and then thank you for your effort and then thank you for your attention and then thank you for your hard work for this course. And then okay, thank you everyone. 감사합니다.